So up to this, we will able to know that how to determine the excess and limiting reactant and how to calculate the percent excess reactant. Good afternoon, everybody. Today's lesson is the continuation of the chemical process calculation. And in this lesson, we will describe the term conversion, yield, selectivity, and process calculation in combustion reaction. Now, conversion never goes to the completion. The chemical reaction occurs in the given system till equilibrium is established between the different constituents, reactants and products. The reaction can never be carried out to a conversion beyond the equilibrium value. So it is the conversion. Conversion is the fraction. Conversion is actually the fraction of feed. Fraction of feed that is converted to product. Now, percent conversion is calculated as moles of feed reacted or consumed divided by moles of feed charged into 100. It is basically the degree of completion of reaction, that is conversion of limiting reactant. Now, the reaction frequently the reactants enter into the different other side reactions also. So for this the terms yield and selectivity comes, and the terms yield and selectivity indicate the degree to which the reactants are converted to desired products. So the yield is represented as percent yield, and percent yield is calculated. Yield is calculated as moles of reactant converted to desired product divided by total moles of reactant converted into 100. Now this yield is same as reactor yield, and overall yield or plant yield is bit different with this yield, reactor yield. So it is defined as moles of that is overall yield is defined as moles of reactant converted to desired product by moles of reactant fed to the system or fed to the process into 100. Selectivity indicates the relative prominence of the side reaction over the desired reaction. Selectivity is calculated as the moles of reactant converted to desired product divided by moles of reactant converted to undesired product. Now we will solve one problem to clear the calculation of conversion, yield and selectivity. The problem statement given, we have taken as the earlier problem, the formation of phosgene. So carbon monoxide plus chlorine gives phosgene, and the product contains 12 moles phosgene, 3 moles chlorine and 8 moles carbon monoxide. And assuming the original feed mixture is free from phosgene, so now we have to calculate the percent conversion of limiting reactant. Percent excess reactant is already calculated in the earlier lesson, and again we have to calculate the moles of total product per mole of reactant mixture fed to the reactor. So according to the stoichiometry, to produce 12 moles phosgene, 12 moles carbon monoxide and 12 moles chlorine reacts. So therefore original reactant mixture contained 12 plus 8, that is 20 moles carbon monoxide, and 12 plus 3, that is 15 moles chlorine. Stoichiometric ratio of carbon monoxide and carbon monoxide and chlorine is 1 is to 1. Now your percent excess carbon monoxide calculation is over in the earlier lesson. Now we will calculate the percent conversion of chlorine. Actually, chlorine, the moles of it, it is calculated as moles of chlorine reacted divided by moles of chlorine charged into 100. So moles of chlorine reacted is 12 moles and moles of chlorine charged is 15 moles. So 12 by 15 into 100, it is 80%. Now for the third part, that is total moles of product. Total moles of product gives 12 plus 3 plus 8, that is 23 moles, and total moles of reactants is 20 plus 15, that is 35 moles. So moles of total product per mole of reactant mixture fed to the system is 23 divided by 35, that is 0.657. Now come to the second problem. To calculate the conversion, yield and selectivity, everything. Now we will consider the vapor phase hydration of ethylene to ethanol, and diethyl ether is obtained as a byproduct. So two reactions is given, that is ethylene plus water gives ethanol, and 2 moles of ethylene plus water, it gives ethyl ether. A feed mixture containing 60% ethylene, 3% inert and 37% water is sent to the reactor. The product analyzed, after analysis of the product percentage composition is given. Ethylene, ethanol, ether, water and inert, every percentage is given. Now we have to calculate the conversion of ethylene, yield of ethanol and yield of ether based on the ethylene. So we have the feed mixture composition and product mixture composition. Now basis of the calculation is chosen 100 mole of feed mixture. 100 mole of feed mixture. So we can tell that in the feed mixture ethylene is present 60 mole, water 37 mole and inert is 3 mole. Now as inert material does not change in the chemical reaction, so inert material can be considered as the key component of the reaction. So inert balance is product, if we consider the product amount is P, so P into that inert percentage, it will be equal to the inert present in the feed mixture, that is 3 mole. So here from here we can calculate the P, that is the product amount of product in mole. So P equal to P comes from this calculation, P comes 83.57 mole. The product contains, now we can calculate, whenever we calculate product amount, so now we calculate the every component of the product present in the products in mole. So ethylene present in the product is amount of product into the percentage of ethylene present in the product, and ethanol also the product amount of product into percentage of ethanol present in the product, and ether amount of product and percentage of ether present in the product, and similarly water and inert will be the same. Inert is the 3 mole. Now we will calculate percent conversion of ethylene. Percent conversion of ethylene is calculated as moles of ethylene reacted divided by moles of ethylene charged. So moles of ethylene reacted is initially in the feed moles, ethylene mole is present 60 minus and 45.04 is present in the product. So 60 minus 45.04 is reacted, ethylene reacted. So 60 minus 45.04 divided by 60 into 100, that is coming 24.93%. Now yield of ethylene, yield of ethanol. is calculated as moles of ethylene converted to ethanol divided by total moles of ethylene converted. So moles of ethylene converted to ethanol is ethanol present in the product stream, that is 12.01 mole. 12.01 divided by moles of ethylene converted, that is 60 minus 45.04 into 100, that is 80%. Yield of ethanol is 80%, and yield of ether is moles of ethylene converted to ether divided by total moles of ethylene converted. Now, if we see the chemical reaction, so for production of ether, 2 moles ethylene is required. So 2 into 15 mole by divided by ethylene converted, that is 60 minus 45.04 into 100, it comes 20%. So yield of ethylene ether is 20%. Here multiplication of 2 is required because 2 moles of ethylene required for 1 mole ether production. Now, material balance in combustion reaction. Combustion of solid, liquid and gaseous fuel. Almost all process energy requirement is met by combustion of fossil fuel. Fossil fuel consists of mainly carbon and hydrogen with small amount of oxygen, nitrogen, sulfur, mineral material and moisture. The composition of fuel varies widely depending on the types and source of fuel. So combustion calculation are carried out to relate the quantities and composition of the fuel to those of the flue gas. Now, for calculation of combustion reaction, we need to know the three terms: theoretical oxygen requirement, excess oxygen, that is represented as the percent excess oxygen, and net oxygen. Now, theoretical oxygen is the oxygen requirement for burning of all carbon present in fuel to carbon dioxide and all hydrogen to water. Now, the oxygen comes from the supplied air. Oxygen comes in the combustion reaction from the supplied air. To ensure complete combustion, usually more air or excess air is supplied than the stoichiometrically or theoretically required amount. Now, percent excess oxygen. It is the oxygen supplied through air in excess of stoichiometric or theoretical requirement. In excess of theoretically requirement for combustion. Percent excess oxygen and percent excess air are the same. Then net oxygen. If oxygen is already present in fuel composition, the percent excess oxygen is based on the net oxygen. It is the total oxygen required for complete combustion minus oxygen already present in the fuel. For process calculation of combustion of solid fuel, so fuel component balance is required for material balance. Now, first is carbon balance. Carbon balance, in the carbon balance, all the carbon present in the flue gas, that is exit flue gas, comes from the fuel. Then S balance, that is the inert material balance. S can be considered as the key component of the reaction, as it is not changing after reaction. So the amount of refuse formed or some unburned carbon is present in the S balance. Then nitrogen balance. Nitrogen in the fuel plus nitrogen supplied through air will be equal to the nitrogen in the flue gas. Then oxygen balance. Total water present in the flue gas is made up of water produced by combustion of hydrogen plus moisture present in the fuel and supplied air. So moles of oxygen used for burning of hydrogen will be equal to moles of oxygen in the fuel and air minus moles of oxygen in dry flue gas as carbon dioxide, carbon monoxide, sulfur dioxide and free oxygen, etc. Now we will explain one problem to calculate the percent excess air and propane, how much fuel is burned and composition of the flue gas. Now problem statement is propane is burned with excess air to ensure complete combustion. If 55 kg of carbon dioxide and 15 kg of carbon monoxide are obtained when propane is completely burned with 500 kg air, determine the mass of propane burned, and number 2 the percent excess air, number 3 the composition of flue gas. So for solution, the basis of calculation we consider 55 kg carbon dioxide and 15 kg carbon monoxide obtained by combustion of propane with 500 kg air. Now, see the schematic diagram of the combustion process. Fuel is propane. Propane, consider the F mole of propane is supplied for the combustion. Then air supplied is given, that is 500 kg, and product in the exit product is also given, that is carbon dioxide 55 kg, carbon monoxide 15 kg, and water may present in the flue gas. Now to find out the propane, how much propane is burned or propane is supplied for the combustion. So you have to first calculate the exit composition in the fuel gas, in the flue gas. The 55 kg carbon dioxide and 15 kg carbon monoxide. So moles of carbon monoxide and moles of carbon dioxide present in the flue gas is to be calculated. So moles of carbon dioxide in the flue gas will be 55 divided by 44 molecular weight of carbon dioxide, and moles of carbon monoxide present in the flue gas, that is 15 divided by molecular weight of carbon monoxide 28. So these moles are coming, and air supplied is given 500 kg. These also converted to kilomole. So 500 divided by average molecular weight of air 29. 500 divided by 29, it comes 17.24 kilomole. Now to find out the mass of propane burned or fuel burned, we have to consider the carbon balance. Now moles of carbon in the inlet fuel will be equal to the moles of carbon in the exit flue gas. So considering the balanced stoichiometric equation, C3H8 propane is C3H8. C3H8 plus 5O2, it gives 3 carbon dioxide plus 4 H2O. So 3 moles carbon is present in the propane or fuel. So 3 into F mole. F mole is considered for propane to burn. So 3 into F, it will be balanced to the total moles of carbon present in the flue gas. So 3 into F will be equal to the 1.25 plus 0.055357. So from here F can be calculated, that is moles of propane burned can be calculated, and mass of propane can be calculated as moles of propane into molecular weight of propane. So it is coming 26.23 kg. So question number 1 is solved. Now question number B is for the percent excess air. You have to calculate the percent excess air. Now considering the balanced stoichiometric equation, according to the stoichiometry, 1 mole propane requires 5 mole oxygen for complete combustion to produce carbon dioxide. So therefore theoretical oxygen requirement to burn given propane is 5 into the moles of propane burned, that is 0.5952. So it will come to 0.976 kilomole. Now theoretically requirement of air, uh, it it comes from the composition of oxygen in air. So composition, that means percentage of oxygen in air is 21%. So theoretical requirement of air is 100 divided by 21 into theoretically required oxygen. So it gives the theoretically required air. So it is coming 14.17 kilomole. Now your supplied air is 500 divided by 29, that is 17.24 kilomole. So excess amount, air excess is 17 point, your supplied amount minus theoretical amount, that is 17.24 kilomole minus 14.17 divided by theoretical amount, that is 14.17 into 100, it comes 21.67. So up to this you learned today. And composition of flue gas, every composition every composition or every component present in the flue gas will come out from the material balance or from the component balance of fuel. So it is bit lengthy and it will be discussed in the next class.